Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We are happy to have Amir Shpilka, who used to be at the Technion. No, he's at Technion, but he's here for the year. And he is going to talk about on the Fourier spectrum of symmetric Boolean functions.
Thanks, Jennifer. So yeah, it's great to give this talk, to open the seminar season. Yeah, to lower your expectations for the remaining talks. And yeah, okay. So what I speak about falls into the theme of analyzing Boolean functions. So what we do in analysis of Boolean function, we pick some representation of Boolean functions. In this case, it's going to be the Fourier transform. And I will not define it now, but I'll just mention that the Fourier transform of a Boolean function is basically a way of writing the function as a polynomial over the reals. That's it. We later give the formal definition, but that's it. Just write the Boolean function as some polynomial over the reals. And what we do is we start asking questions about this representation. We ask about the coefficients. Are they all supported on low degree monomials, on high degree monomials? What's the degree of the polynomial, etc.? So this is a very general question, right? If we cannot say anything meaningful if we ask the question about all Boolean functions. So instead what we do, we usually focus on families of Boolean functions. And for example, family Boolean functions that are computed by small Boolean circuits, like this talk, it's going to be symmetric Boolean functions. You just restrict yourself to some natural class of Boolean functions, and you try to see whether there's one common theme to all the functions in the family. In this talk, I'm going to focus on the Fourier spectrum of symmetric functions. Good. So what's the motivation for studying such properties of Boolean functions? So I still did not define symmetric functions, and I did not define the Fourier transform, but I'll just give some high-level motivation. Well, if you can say something meaningful about the representation of the function, then it will have many applications, because such questions appear in cryptography, and we will see one such question in cryptography. The questions are also very, they appear a lot in learning theory. You'll also see an application to learning theory. And of course, they're important to circuit law bounds, pseudo-randomness, voting theory, and much more. So those questions are very, very natural. And I hope that I will convince you during the talk that these are important questions. Okay, so what I'll do, I'll first define the problem. I define what the Fourier transform is, what symmetric functions are, and what is the question that I'm going to study. And then I'll give one application of this question to the scenario of learning symmetric juntas. And because this is a seminar in theory of computing and not a general talk, there will be proofs, many proofs. One proof, but in many parts. Okay. So let's begin, and the first thing is symmetric Boolean functions. So in contrast to common belief, symmetric functions are not the constant function, not necessarily. So symmetric functions are functions that are invariant under any permutation of the input bits. So if you take any permutation sigma, and you permute the inputs, so you don't change the number of, you just change the order that they appear, still the value of the function remains the same. Okay? So I'll sort of give two examples, but another way of thinking about it, because we are dealing with Boolean functions, so if we have a certain number of ones, we can just think about all the ones being at the beginning and then zeros, right? So basically the function just depends on the number of ones in the input or the weight of the input. Okay, so that's a different way to define symmetric Boolean functions. So in other words, you can, for each symmetric Boolean function, there is a corresponding polynomial, or a function that takes as input the weight 0, 1, 2, up to k. Yes, we have k variables. I did not mention that k is the number of variables. So the weight can range between 0 to k, right? If you have 0 ones or k ones. And this is just another way of representing symmetric functions. Okay, and we'll always think about, I'll have the subscript n to denote when I think about it as a polynomial over the integers, and without it, it's going to be a Boolean function. But if there are typos, don't be confused. It's the same thing, okay? Good. So what are examples? Well, many examples, right? Famous function, parity function, invariant other, just depends on the number of ones, majority, and, or, okay? And there are more functions. Excellent question. It will become clearer during the talk. No, but that's, it used to be F. It used to be, no, it's, let's see if someone can figure this out.
Sort of the same as an unlabeled graph, right? You don't want the labels to matter. Once you have
so graphs, for example, are functions that are invariant. So these functions are invariant under the action of any permutation. Graphs are invariant under actions of permutation acting on edges, right? So it's Sn acting on pairs of. It's slightly different kind of function. Right? You acting Sn acting on the nodes, but the action on the on the edges is slightly different. So, right? But yeah, it's invariant under a different permutation.
But sort of, popular one could just say it's anonymous functions. They shouldn't depend on the label of the post.
Right. Yes. Good. Okay, so these are symmetric Boolean functions. Let's define the Fourier transform. So to define the Fourier transform, it's somewhat more convenient, instead of working with the 0-1 representation, to work with the -1-1 representation. So we just identify 1 with -1 and 0 with 1. Okay, and the Fourier transform, as I said, is just a representation of the function as a polynomial over the reals. So what does it mean? So you have the function, and I can write it as a polynomial. Now, since -1 squared and 1 squared are 1, the polynomial might just be a multilinear polynomial, right? No variable should appear at degree 2 because it's useless, right? So we have some coefficients, which we call, so for every subset of the variables, we have the multilinear monomial, and the coefficient is called the Fourier coefficient of the set S. And for short, instead of having this monomial, I'll just denote it by x to the s. Okay, so this is the Fourier transform, that's it. Okay. So for symmetric functions, what can we say? Well, if G is symmetric, then it's easy to verify that the Fourier coefficient of a set S only depends on the size of S, right? Because anonymity, right? There's no every two sets of size S are the same as far as the function is concerned, right? Good.
Is it clear that it translates to the Fourier domain?
Yes, so there are several ways of seeing it. One of them is just saying obvious. The other way is proving it. And to prove, you can just take the function and apply any permutation on it. So it will permute the coefficients, and then you take the average, you'll get the same function because the function remains the same. So that's another proof. Okay, so here's two examples. So the parity function. So the parity function is extremely nice because in the -1-1 representation, if you want to compute the parity, it's just like multiplying the variables, right? So the parity function, this is the Fourier representation of it. This is the Fourier transform of the parity function. Okay, and I even went down and computed the Fourier transform of majority, and you can verify it. That's the Fourier transform of majority. So in parity, there is only one non-zero coefficient, and it's 1. In majority, all the coefficients are either plus half or minus half. Yes, and it's the 1 minus 1 majority, right? Not the 0-1 majority. Okay. Good. Okay, so this is the Fourier transform. So what kind of questions do we want? Sorry.
In the majority, some coefficients are 0, the square ones, the ones with 2 variables.
Yes, some coefficients are 0. Yes, so yeah, I just mentioned the positive coefficient, the non-zero coefficients, yes.
Same with parity.
Okay. Thanks, Ladu. Okay, so yeah, usually during the talk, I will have a little box at the top which basically summarizes what we've just said so that we'll have some reference point. Okay, so what are the questions that we are studying? So in this talk, there are two. If IFF is if and only.
G of S depends only on S, then G is symmetric?
Yes. Good. Okay, so here are two natural questions.
PowerPoint.
Sorry?
Yeah. You don't know how to do that.
I know how to do it, but it's a new theorem. No, so
It's true. Let's go on.
yes. So okay. So there are two questions that we will that are interesting in that respect, and we'll only study one of them, but I'll mention both of them. The first question is, given a symmetric function G or any function G, what can you say about the degree of the Fourier spectrum? Means, what is the maximal monomial that has a non-zero coefficient? That's one question. The opposite question asks the following thing. So let's ignore the free coefficient, okay, the constant term. So what is the minimal term, the minimal set S that has a non-zero coefficient? Okay, so it's like asking about the two opposites of the Fourier spectrum.
In your examples already showed that the answer, the maximum is n and the minimum is 1.
Exactly. But
for those
But I will ask about the extreme case in what is the minimal possible maximum and what is the highest possible minimum. So, okay. So, right, so this is what the question asks. So the question asks, what is the minimal S such that you are guaranteed that for any symmetric G? You can, of course, come with symmetric G with low minimal term. But what is the worst? So parity is the worst, right? Because it doesn't have any low order coefficient except the top. So let's rule out parity. What can we say now? Parity is very extreme, right? It has only one Fourier coefficient. So this is the question that we will be focusing on. And just the two questions seem very different because they speak about the two extremal cases. But actually, for some functions...
If this new theorem is true, that it's...
What is the new theorem?
That this error can be turned around.
And symmetric if and only if.
Okay.
And only if, then I just take, okay, so you rule out parity, so I make up the next one, which is x1 up. I mean, I just take...
Boolean.
Won't be
Or
symmetric.
symmetric or Boolean.
Symmetric and Boolean function. Boolean is very important.
I thought it's symmetric if and only if...
But it's not necessarily Boolean. It's going to be a symmetric function, but not necessarily Boolean.
Values plus minus
Yeah.
1 on the key.
So the theorem has a caveat, right? Good. Okay, so let's see something that's it may be confusing, but let's try to do it. Maybe I'll do it on the board. So think about a function that does not have a constant term, right? The empty coefficient means the one monomial, right? The monomial that ones. So it doesn't have any free coefficient. Now, I want to say that the degree of the minimal term in that function is the same as the degree of the function G plus parity. And I can just, do it, sketch it on the board for a second. So if we have two Boolean functions and we take their parity, then in the Fourier domain, it translates to multiplication because parity is multiplication, right? So now if parity is x1 times x2 times xk, if you multiply it by any monomial, or as we called it, x to the s, then because of multilinearity, this translates to x to the complement of s, right? So if a monomial was of degree L, it becomes of degree k minus L, and vice versa, right? So a minimal term becomes the highest degree. So these two questions are closely related, right? Because if G is symmetric, this is also a symmetric function because it's the parity of two symmetric functions. So the questions are related, but they are not the same because we have this extra condition. Okay, so questions different but related. And as I said, in this talk, I will focus on the second question, and I'll show because it has some nice applications. Okay?
I see. So when you say the minimal Fourier term, then that's the same you're saying as maximal Fourier.
No, only if you don't have this thing. Because if this term is not zero, then when you solve with parity, you'll get the top coefficient will be full degree.
You get the top.
Okay.
So for functions with this thing equals 0.
So no,
Okay.
no, it's just there are two different functions. One of them is G, the other function is G. So parity, and I just say that if G does not have doesn't have the constant term in its Fourier spectrum, then the minimal term here is the degree here, and vice versa. That's some observation to play a little bit with Fourier transform. That's it.
Is this question less interesting if S can be the empty set? Or
Yes, it's because it's the bias and
S could just be a constant function?
yes. Yeah, I mean, we rule out the constant set because it's well, I mean, it will not have any applications, for example, in what we'll show. So it's just not an interesting question. Okay, so good. So remember, we have to rule out the cases that G is parity or not parity because then we don't have any minimal term, right? So that's one thing. Okay, so this question turns out to come up also in cryptography, but not for symmetric functions, but in general. And yeah, I learned it from a referee of the complexity conference that mentioned this. So it's very nice of the referee, in case he's sitting here. Okay, so what are correlation immune functions? So we say that a function G is T correlation immune, okay, if you look at any subset of T of the variables, and no matter how you fix it, it doesn't have any effect on the value of G in some sense. So what does it mean? In other words, the probability that g equals 1 remains the same no matter how we fix any t variables. So you cannot affect the probability that g becomes 0, 1 by constraining only t, putting constraints on t variables. No, that's correlation. At least that's what Google says, and the Wikipedia, and also the articles, the original articles. I also looked. Yeah, I'm not. I'm not a teenager. I'm still reading articles. Sorry, Bing. I should have said Bing. Sorry. Oh. That's what Bing says. Yeah, sorry. No, Wikipedia. It's not Google. It's just Wikipedia. No. So okay, no. But anyway, so. And these questions come from the motivation of the security of combining functions for linear feedback shift register. So basically, if a function is not correlation immune, then by trying to fix a certain number of variables, you can learn something about the functions, and you don't want it to happen. It's bad, right? So that's where it comes, and it was defined by Siegenthaler. And a very interesting property, which we'll later prove, is the following. This is the following is a theorem by Shao and Massey. G is T correlation immune if and only if all small Fourier coefficients are 0. So the question that we are basically asking is about how correlation immune is the worst symmetric function in some sense, right? Because if the worst function is a low degree term, then it's not very correlation immune, right? So that's you wait for the proof. But, yes. Yes. Yeah, okay. You ruined this part. Yeah. It's very easy. Okay. So, and this is, right, so recall. So this is the question that you ask, and basically it's the same thing, right? Asking how correlation immune are symmetric functions. Okay? So that's one connection to cryptography.
It's like an old theorem, right, or something?
Okay, it's calling it theorem is fun, right? It was a paper proving this theorem, but it's one line. I mean, both directions are the easy direction. Okay, so
Like related to Ty's independence and
don't. I mean, it's trivial. It's just the fact that if a polynomial is non-zero, there exists a value that makes it non-zero. I mean, that's basically the proof. Anyway, good. So here's another application: learning juntas. So let me describe the problem, and then I'll say what the application is. So what is the problem of learning juntas? So it's also called the learning in presence of irrelevant features. So in the learning scenario, think about the PAC learning model. So we have some unknown function, age, that depends on n variables, not k, n variables. But we know that not all of those variables are relevant. Namely, that there exist k variables among those variables, such that age only depends on those variables. So namely, there is some other function g, such that age of x1 to xn is just g evaluated on those variables. Okay? So that's a k junta. It's a function of n variables, but only k of them are relevant. And the learning problem is the following. So we get examples from that are drawn from the uniform distribution. So you get x and age of x. And from those examples, we have to understand what the relevant variables are. Of course, this has to be done with high probability because it can be the case that you always get the same examples, so you learn nothing, right? So this is a question with high probability. So again, there are k relevant features, you get examples, and you want to understand what the variables are. So what's trivial? The trivial is to basically, okay, let's guess what are the k variables. So you have n choose k possibilities, and if you know what the variables are, you can easily verify that these are the important variables. But this takes time, roughly that time. Okay, I'm forgetting about over k factorial. If k is small, this is roughly the time. So the goal is to do much better than this. And you have a lower bound which says that you need 2 to the k samples, basically.
It's n to the k.
N choose k. Yeah, I mean, this is something. You always throw this just to make yourself sure, secure.
I don't understand. N to the k is a polynomial in n.
Think of k
K is log n or log n or something, or polylog.
I see.
Okay. Oh yeah, if k is log, then this is quasi-polynomial, this is polynomial, and k is constant also. It's, good. And Avram Blum calls this function the most important function in computational learning theory. And I think that it's obvious because if you can't even tell which variable is relevant and which not without trying all possibilities, then what can you do, right?
It's even more broader, right? Because I mean, the goal of learning theory is you forget whatever you know and you just throw all the data that you have at the machine and say, figure out what's relevant.
Yes. Yeah, and this is actually, it's also a practical question, right? You go to a doctor, you tell him, yeah, you know, yesterday I ate bacon, 2 days ago I ate egg, today I have fever. What's relevant? Is it the combination of bacon and egg? What? So, yeah, it's a very practical question. And it's not symmetric, right? Because you cannot replace bacon by egg, or if you had a car accident the same day, it's maybe more relevant, but yeah.
For appropriate progress, Avram also has a $1,000 prize.
Yeah, I want to keep it to myself. I didn't. But yeah, good. So let's see what's known. So this is the problem, okay? So here's a simple algorithm. It's not manual, it's just out there. The algorithm says the following. Try to learn all Fourier coefficients one by one. Start from the sets S of size 1, go to sets F of size 2, etc. And the point is that it's not difficult to show that if a Fourier coefficient is non-zero, then all the variables in S are relevant. So if you could peel off variable by variable, it would be great. Right. So, of course, remember, all we get is example from H, so examples of H. So we don't have access to G. So all we can hope is to learn the Fourier coefficients of H, but they will come, of course, from the Fourier coefficients of G. Good. So how do we estimate the H hat of S? Well, that's easy. I mean, it's just a Chernoff bound because it's an average. I didn't show you the formula for computing the Fourier coefficients, but it's a very simple thing, and it's basically the expectation of some bounded function. So it's easy to compute. Good. So what will determine the running time of this algorithm? Well, if we only knew that there was a small set S, then like that S of size at most 100, then this will give us a guarantee that we will not have to run more than n to the 100 time before we find such a set, right? This is the number of sets that we will have to try until we find a non-zero Fourier coefficients. This is why the problem is related to learning juntas, right? Because if you could prove that a non-zero Fourier coefficients exist at a low level, you'll get fast learning algorithm. For symmetric juntas, exactly. Yeah. Okay, so what's known about the Fourier spectrum of juntas? So
Parity you can do with a different way.
yeah, I mean, we assume the function is not parity because parity is just solving a sort of linear equations, which is you can just write at the beginning and then go to the other case.
So you assume the G is symmetric and.
So this is the general problem of learning juntas. When I will speak about symmetric juntas, yes, I will assume that the underlying G, the unknown G, is symmetric. H, of course, will not be symmetric because some of the variables are not relevant. So for the case of symmetric juntas, G will be the symmetric function. Yes, thanks. Okay, so what's known about the Fourier spectrum of symmetric functions? So what about the minimal degree? So the first work on that improved the junta algorithm was done by Mossel, O'Donnell, and Servideo. So they studied general juntas, but they also had a result they also had a result on symmetric functions, and then they proved the following term that if you look at a symmetric function G, then it always has a non-zero coefficient of size at most 2/3 k. Okay? This was greatly improved by Kolountzakis, Lipton, Markakis, Mehta, and Vishnoi to S, which is at most k over log k. Okay, so this was linear in k, and this is sublinear in k. Okay. Now, as he mentioned, there is also the question of bounding from above the degree, and I want to mention it because somehow it uses related techniques. So von Zurgat and Roche studied this problem, and they proved that for any symmetric G, which is non-constant, any function must have high degree. And this is a very funny constant, and it will become clear where it comes from in a few slides.
In particular, any unbiased function by your connection before.
Exactly. So if we look at functions that does not have constant terms, then this result guarantees by the connection that you show that they have a Fourier term at that size.
Much better than.
Yes, much better than k. Yeah, but in general, you cannot assume anything about the bias of the function, right?
So symmetric and unbiased may end up being very small set. So it's also
yes, that's yeah. And one interesting thing, it's a conjecture that nobody knows how to attack today, is that they actually conjecture that the degree should be k minus a constant.
I guess there's never a way to say what not to say.
Yes. Yeah, k minus a constant. Yeah. So the best example today that we have is k minus 3. We don't have any example of a symmetric function of degree k minus 4. And the people that tried computer search tell that this is what's happening until k equals 128, and then they stop. So, yeah. Okay, good. So this is what's known. What does it imply about juntas? Well, exactly the same. So remember, the goal in juntas is to do better than this. Now, first I'll tell you what's known for general juntas, just as a general thing. So Mossel O'Donnell's video proved that you can learn symmetric general juntas in time n to the omega k over omega plus 1, where omega is the exponent for matrix multiplication. So because this is just balancing two different algorithms. So this runs in time roughly n to the 0.7k. And even if omega is 2, so you get the best possible matrix multiplication algorithm, then it will give you n to the 2/3 k. Okay, what about symmetric juntas? So the two results that we previously showed give this kind of algorithms, because it really depends on the size of the smallest s. That's the best thing we know today. That's, I mean, the trivial algorithm following Fourier spectrum, that's the best we know today about juntas. Okay. And as I say, it's the same algorithm, just the analysis is different. Just say, okay, you don't have to run it that much because you'll find the set S earlier. Right? That's the difference. Okay, so let me describe our results.
You can't assume that your symmetric function is unbiased in this learning?
No, it doesn't matter.
So he's proving.
No, this is a theorem, no matter what the bias is.
No, for the learning problem, there's no way to assume that it's unbiased.
No, but first of all, you can learn the bias pretty good. But even if it's unbiased, I mean, so what?
But then you get k to the 0.5.
No, you don't, because you don't know which parity. I mean, oh, if you know, no. So if you knew it's biased, then yes, but yeah.
But you,
yes, but you cannot assume it.
There's no way to get rid of the bias.
No, because you want to keep the function symmetric, and you cannot do it in oblivious manner. So yeah. Okay, so what are our results?
I mean, for weak learning, if it's biased, then you're done.
Okay, yeah. So we proved the following. So we proved that there exists a set of that size, no matter whether the function is biased or not. Okay, so we remove the condition on the bias. Okay, and this improves this one. And this is something that's always fun to have. If you assume the extended Riemann hypothesis, then our algorithm, then k to the 0.5. Sorry?
Then you get a 25% discount.
Exactly. Yes. Yeah. Okay. And for symmetric juntas, it immediately implies the following, right? It implies. Thanks, Sev. Yeah. If you're asking yourself why have students, because you live up to this moment, right? Good. Okay. So, so this gives a running time of n to the k to this 0.525, and just we have to say when the result is tight. So it tights for such case, because then 2 to the k and this number, I mean, somehow collide. So, yeah. So it does give something meaningful. I mean, even this this improvement. Okay, and just as we mentioned, I mean, previously von Zurgatten and Roche implied that if the bias is 0, then you have this result. So what you actually have to study is what happens when the function is biased. But our result, I mean, it works in both cases, but just as a...
So in particular, you also, under the ERH, you also improve the...
Yes, but actually this result, there is a stronger conjecture than ERH, a conjecture that's not implied by ERH that will give here poly-log k. But it's called Kramer's conjecture. But
in your setting, it doesn't...
Not yet. But it's future generations will figure that out.
What's the conjecture for the minimal term in the Fourier terms?
I will not make a conjecture, but I will cite other people. So extrapolating from von Zurgatten-Roche conjecture, it will be a constant.
Oh, really?
So you get polynomial term.
So even
for
if
symmetry.
it's biased, it's only constant.
But it's not my idea. I mean, if it's not true, that's not me.
Sure.
Somebody.
By the way, what happened in the Mossel, O'Donnell's, or video result? There was no relationship between the symmetric case and the asymmetric case?
No, so for the asymmetric case, you have to balance two things, but in the symmetric case, you just run one of the algorithms.
And in your case, there's no such balancing application?
No, nothing. Just you prove something about the minimal Fourier term. Because they either learn the Fourier coefficients or solve the system of linear equations over GF2, but you don't know much about the degree over GF2, but you do have some information about the Fourier. And, yeah. Okay, so as you can see, this is the serious part of the talk now. So no jokes anymore. Okay, so this is what you want to do, right? You want to prove that any symmetric nonlinear meaning not parity, nor negation of parity, is a non-zero Fourier coefficient at that level. Okay, that's what I want to prove. But first, for something which is not completely different. Okay? Just to give some intuition for why the proof goes like it goes. Okay. And what we'll do is we'll prove this result of von Zurgaten-Orsche. And it will fit in this slide. It's not the proof that they gave. Yeah. It's a shorter proof. Okay, so here's a fact. And what is the fact? The fact says the following. Basically, it says that if you have a polynomial over the integers, so from integers to integers, never mind whether it came from a symmetric function or just a polynomial over the integers, you can represent it in this basis. So let me just write what the basis is. So when I say x choose I mean the polynomial x times x minus 1 times x minus I plus 1 divided by, okay, this will look bad, I factorial. Okay? So yeah, let's look at the, okay, L, yeah. Yeah, because I'm thinking about x as a Boolean input, so, but this is it, yeah, I mean, that's y.
And you can write.
Okay, so it's a polynomial, right? Because it's a degree L polynomial, and because you know properties of binomial coefficients, it always takes integer values.
Cancel, or?
Sorry?
No. So
No. So this always. So look at it. I mean, this always take integer values, and there exist coefficients. So this is just the basis for the space of polynomials because you have polynomials of each degree, right? Degree 1, degree 2, etc. And the interesting point is the coefficients will always be integers. And how do you prove it? By induction. I mean, just the coefficients are basically linear combinations of the values of the function, and the coefficients in the linear combinations are again binomial coefficients. I mean, I had this given as an exercise when I was undergrad at the university, so it's something, it's not difficult. But let's use the fact.
Sorry, this assume that g sub n is integer value.
Integer value. It's a function from integers to integers. Okay, but in our case, it's from 0 to k to 0, 1. But in general, from integers to integers. Okay, and so let's prove the von Zurgaten theorem. And first, I want to prove it for the case that the number of variables is p minus 1, where p is a prime number. Why? You will soon see. Okay, so let's start with this simple case. Okay, and now I'm going to define, I'm going to work modulo p. Yes, f has come, but that's not the reason I didn't use it before. Yeah, the end of the talk, I'll tell you. Okay, so let's define the following functions. So I'm going to eventually work modulo p. So define the fi of x, which will be the characteristic function of I, basically. If x will be equal to I, then this will go down and you'll get 1. And if x is j different than I, then modulo p, this is Fermat's little theorem, this is 1. So we'll get 0, right? So in other words, modulo p, we can write g in the following way, right? It's fi of x times gn of I, right? That's the thing. Okay, good. Nothing spectacular so far. What is the coefficient of the leading monomial? Well, look at it. At fi of x, the coefficient is what? It's minus 1, right? Because you just expand this thing and you get minus 1. So in this term, it will just be minus of the sum, right? Now, how many sums do we have? So what about I? I can go between where to where. So either I have 0 1s or 1 1 or k 1s and k p minus 1. So I ranges between 0 to p minus 1. So basically, you sum p different values. And those values are always either 0 or 1, right? Because we are dealing with Boolean functions. So if you sum p values that are 0 and 1, so the only way that you can get 0 modulo p is if all of them are 0 or if all of them are 1. But this means that the function is constant, right? Either it's always 0 or it's always 1. So if the function is not constant, this coefficient is not 0. Okay. So, but this is modulo p. Why can we take modulo p to this representation? Well, think about it. I is at most p minus 1, right? The number of variables is p minus 1. So I factorial is invertible modulo p, right? So this is also the representation over p, right? So it has the same degree. Right? I want to compute, this is equality mod p. I'm claiming that this is the same representation modulo p. I mean, if you just reduce everything mod p. And the point is that I factorial is invertible modulo p because I is smaller than p. So the degree modulo p is p minus 1. Therefore, this degree is also p minus 1. And this is the full degree, right? So in the case where the number of variables is p minus 1, the polynomial is full degree. Okay, but what if the number of variables is not p minus 1, we'll now use density of prime numbers. And here's where 0.52 comes into play.
The degree of this polynomial in this representation is
Yeah, it's the same. The degree can only go down, but since it's full,
it's the degree of the Fourier.
yeah, okay, that's great. I was expecting this question. So this is not a Fourier representation, right? It's a different representation. But the point is that you can move from this to the Fourier by a linear transformation. And linear transformation can do bad things to low order things, but it always keeps the degree the same. Right? It can change a lot the low degree terms, but the maximal degree remains the same. So yeah, great. So and here's where 0.525 comes into play. There's a series of papers that shows that no matter what k is, there's always, or k large enough, right? So this will be meaningful. There's always a prime number in this interval. And the extended Riemann hypothesis basically implies that there exists a prime number in that interval. And Kramer's conjecture says that there exists a prime number in the interval k minus log square of k in k. And if you knew this, and this is really, you just need to find the closest prime, and then you get something about the closest prime is more than k. So that's the mysterious 0.525.
That still doesn't get it down to constant.
No, it will not get it down to constant. So you need some other argument. This is not good enough to get down to constant.
But it seems like maybe natural. I don't
So, is it clear why this statement is helping? Why does the existence of the prime here help?
Yeah, because you can just set a few variables to 0 or to constant without changing the degree. And then you'll have only a number of variables is p minus 1.
Okay,
so you can always set, you can set small variables. You can only lose a little, you can lose
the remaining guys.
You will set some variables to constant without making the function into a constant. And this can only kill your reduce your degree. So, excellent. Good. So what did we learn from this thing? So we learned that working modulo prime numbers can give us useful information. Right? In this case, it was the information that p numbers can sum to 0 only if they are all equal. Okay? If numbers are 0 and 1. Right? Okay. But in general, we will do a lot of calculations modulo prime numbers, and this can be viewed as some motivation to this approach. Okay. So let me give you an overview of the proof. Yeah, I don't have, how much time do I have? I don't have a clock.
20 minutes.
Oh, I can give 7 proofs. Okay. So our starting point will be the assumption that G does not have small coefficients, small non-zero coefficients, or coefficients that are supported on small sets. Okay, so by the Shao-Massey theorem, this means that no matter how we fix T variables, it will not affect this probability. Right? This is the theorem that I cited. I will cite it again soon. Okay, from this, what we will do is the following. We will express this probability for any restriction of T variables. So this probability is just some linear combinations of the values of G, right? Because, you just ask yourself, how many values are 1? So just like the sum of values, right? It's just this. Okay, so this will give us some linear combination of the values of G. But you see, if no matter how I restrict the variables, the bias doesn't change, then I get many equations that sum to the same value. So I get a lot of equations in the values of G. And somehow we'll have to say that this restricts G so much that it must be parity or constant. Okay? So from the equation, so the way that we do it is that from those equations, we will deduce that either G is parity or G must be fixed on very large intervals.
This T collusion resilient, whatever,
collision
resilient. So this was true for all T, for your...
No, so if you're T correlation immune, then you have. If setting, it's the same T.
It's the same T.
Yeah. And then, so from this, we'll deduce that if G is not parity, then it must be fixed on very large intervals. And from that information, we'll actually deduce that it must have a low term with a non-zero coefficient, which by our argument is actually, it's actually a contradiction because we assume that it doesn't happen. So, yeah. So this is how the proof will go. We'll start by this thing. We'll just then get many equations. We will analyze the equation modulo prime numbers to get this conclusion, and then we'll get the contradiction easily. Okay, let's start. So I already used the notion without defining it, but the bias of G, let's call it the probability that G equals 1. Okay, there are many ways to define the bias. All of them are different, but equivalent. But this is one of them. And the intuition, so I will...
This is going to be a quantity between 0 and 1. And
yes, just quantity between 0 and 1, yeah. Okay. Now, the intuition for the massive, the algorithm, right, I said we are going to look at many equations where we restrict variables. And if you think about the learning problem, this is very intuitive because in the learning problem, if you look at all the samples in which, say, the first coordinate is 0, then if you see that the bias changes, then you understand that x1 is relevant. Right? So looking at restrictions does tell you something about the relevant variables in the learning. So it gives good motivation to start to trying to study the function when you restrict variables. Okay, so I will need the following notation. And this is an important notation that will appear soon, will appear a lot. I will use this subscript to denote that I'm taking m variables and I'm making r of them 1s and m minus r of them 0s. Okay? So let's say about the last m variables. So among the last m variables, I'll substitute 1s to r of them and 0s to the rest. Okay? And G is symmetric. It doesn't matter. It doesn't matter which variables, and it keeps the function symmetric, etc. Okay? So let's look at examples. So assume that you have the majority on 5 variables, and you plug in 0 to the last 2 variables. So in order for the majority to be 1, all the remaining variables must be 1, right? So what you get is this function, right? That's what you get if you restrict this thing. And of course, this is symmetric, right? Similarly, parity, if you put substitute 7 1s to the last m variables, and now you get a negation of parity, right? Because you have m minus k minus m variables are alive, and then the rest of the variables contribute 1 to the parity, so you get the negated parity. Okay, these are just 2 examples, and so basically over the integers, this is what's happening. So I want to understand how this function look like. So now the input is coming from k minus m, right? Because the m variables already restricted, already fixed, right? And since among the m variables that I fixed, all of them are 1, this value is exactly...
I'm not sure what the notation, the m error r is.
It means that the last m variables got r1s. Yes, this is the substituting r1 to the last m variables.
But r is smaller than m?
Yes.
So you pick...
It's a symmetric function, doesn't matter which variables.
Okay.
Right?
So why don't you have to write x restricted to the set minus the last?
Because I don't, yeah, it's PowerPoint, it's not easy.
So that's what you meant, okay. Yeah.
So let's
Maybe
look.
it's easier just to think about it as this does the definition. You just add r to...
Yes, but then x as a smaller domain.
To be
yes.
like smaller.
Yeah, exactly. So let's look at the picture. So assume that this is the graph of Gn. So at 0 it is 1, at 1 it is 0, this is 0, this is 1. So 1, 1, 0, 0, etc. Okay? And recall this is the equation. So now we want to understand, say, this function. So what happened? Okay, so this is the original function. Now I'm shifting it by 1, right? Because I already know that the minimal weight now will be at least 1 because I already substituted 1 to 1 variable. And so everything shifts by 1, right? Because now the minimal weight is going to be what used to be 1. And now I have only k minus 3 variables because 3 of them are fixed. So I trim the edges. That's it. That's a function. Okay? And this exactly corresponds to this thing. Okay. So what we will know is that if you don't have small non-zero Fourier terms, then no matter how you fix t variables, so all those shifts up to t places don't change the bias. So it will give us a lot of information because you see, it tells you a lot about the weight. Okay, good. So, okay, so these are the definitions. This is the bias, this is the Fourier coefficient, and this is substituting R1 to the last m variables. Okay, these are notations. And here's the theorem of Chow and Massey that I mentioned. So he said that the following are equivalent. You don't have all the Fourier coefficients supported on small sets are 0, is equivalent to the following. If you pick any m smaller than t variables, at most t variables, and any r at most m, and you make this substitution, the bias doesn't change. Okay, what is the proof? Well, the proof is you look at the Fourier transform, and it's...
Just sort of clarify, what is this claim trying to say? It's
trying to say that if you don't have small... Okay, just as the following. If you don't have small... if all the small Fourier coefficients are 0, then the bias of the function change no matter how you restrict t variables. Doesn't change. The bias is the same.
But when you're changing this, t will be small enough so that you're changing things with very...
So t is going to be roughly square root k, the k to the 0.525. Yeah.
But this seems very similar to the correlation.
This is exactly, this is the theorem, it's the same theorem, I'm just repeating it.
Okay.
Okay, and I said I will give the proof, but the proof is here. It's easy to see. I mean, basically what you do is you just write the polynomial and you say that if you have a small Fourier thing, then you can just fix it so that the constant term will change. And it's just some easy property of polynomials. You just, it's nothing, it's really, really simple. Okay, good. So we have this theorem, and this will be our main tool, because remember, this is what I assume, and I want to show that it cannot happen with t that is very large. So basically what I will have to show is that there exists some substitution for t which is not too large that changes the bias. Or another way to say it, I will assume that all substitutions do not affect the bias, and I will get the function must be parity or constant or something. Okay. So I will work with substitution instead of looking at Fourier coefficients. So I think that from this point on, I'm not sure that we'll even see Fourier coefficients. We'll just work with substitutions. Okay. Yeah. Okay, good. Okay, so let's speak about the bias of G. Let's write it. Okay. So here's the bias of G. The bias of G is the probability that G is 1. So let's look at this representation. So at the value I means that we look at inputs of weight I, right? So how many inputs are there of weight I? Exactly k choose I, right? So this is, so since only the G's that are equal 1 affect this sum, right? All the rest are 0. This is exactly the probability that the function is 1, right? You just sum how many inputs give you 1 and divide it by the total number of inputs. Okay, so you see the bias is a linear equation in the values with coefficients that are binomial coefficients. Okay, good. Now, let's look at this function. What happens if I restrict m r to m, right? M less than variables get r1s. So let's write the bias. So now we have only k minus m variables. So I summation I goes 0 to k minus m, but now G evaluated I plus r, right? Because the less variables already got r1s. So what we know is that if the two biases are the same, then we have many linear equations, right? Because for every m smaller than t and for every r smaller than m, this thing must equal this thing. So you get a whole set of linear equations. But of course, the problem is that it's very hard to use this information because you get a set of linear equations, but the coefficients are complicated because they're still binomial. The matrix is not full rank. And the solutions have to be 0, 1, right? Because these are the values of the G's, right? I want to get some information about the values of the G's from this set of linear equations. So I like solving a set of linear equation, but I'm only caring about the 0, 1 solution. So this is, in general, a difficult task.
So I mean, just to understand, so you're going to have one equation for every m
M
and
and
every
R.
r.
Yes, but I'm only going to use some of them.
Okay.
The easy ones. Yes. Good. So this is why it's complicated, okay? So what's the insight that we gained from the previous proof is that working modulo prime numbers can make things easier. And the main tool for us will be Lucas' theorem, which is a very neat theorem, not I don't know whether all of you know it or not, but it's very cute. And it says the following. Take two integers, a and b, and write them in the base p expansion, right? So a is some AIPI, p is some prime number, yeah, and b is BIPI. Then here's the fact, a choose b, modulo p is the same as the product of a choose bi. If you want, I can give you the one-line proof after the talk. It's a one-line proof. It's a smart one line, but it's a one-line proof.
Maybe it's like a long line.
2 lines, if Buzz insists. Yeah, it's really okay. Yeah. Good. So this is the fact. What's good about it? Because it seems that it takes something nice and makes it a product of ugly things. But let's see what we can say. So here are a few examples. Assume that r is smaller than p. Then p choose r is 0. Why? Because what's the expansion of p? P is 1 times p and 0 times plus 0 times 1. R is 0 times p because it is smaller than p plus r times 1. 1 choose 0 is 1. 0 choose r is 0. So this is 0. Great. That's 2p choose r. So it's 2p is again 2, 0. R is now some r1 and r0.
So the equivalence, is mod p.
Mod p. It's equivalence mod p. Yes. That's very important. Yes. So look, so this term will be 0 unless r0 is 0. So this guy is not 0 only if R is 0 or P or 2P. So great. So working modular things can help simplify the equation greatly, because in the previous examples we had a summation of many binomial coefficients. But if this was K, then only 3 of them are important. So all the linear equations become equations on 2 terms or 3 terms, and this is something that my limited mind can handle.
So the main reason you use the Lucas theorem here is to focus on which things are 0 and which ones are not.
Yes, I just want to, look, I use the Lucas theorem to simplify the equations. To, instead of having equations with K terms, I'll have equations with 2 terms or 3 terms. And that's it. And an equation with 2 terms basically tells you, look, this value plus this value equals something. So these 2 values are correlated. That's the way I use it. Okay. So, and the last point, which does not follow from Lucas theorem, but is just an easy calculation, is that P minus 1 choose R, congruent modulo P to minus 1 to the R. And what's this? Because P minus 1 is like minus 1. So you start going, so basically you have minus R factorial over R factorial, but the minus is like, this is some easy calculation. But that's it. And this is also nice because 1 minus 1 coefficients are also something I understand. Okay, so that's the point. It simplifies equations. Okay, so let's throw it at our scenarios, and let's do first a warm-up. I don't know whether it's needed or not. So that's what we assume. This is 0 if and only if, no matter how you fix things, the bias doesn't change. Okay, so here's something, again, like in von Zurgaten, I pick prime, which is very large, right? It's close to K as much as I can. Okay, so just think about P as being roughly K or close to K, and T is going to be small, right? It's just the difference between those. Okay, so recall after fixing T, I will assume that I want to prove that there exists a Fourier coefficient of that size. So I will assume that no matter how I fix T variables, nothing happens. Right? So after fixing T vars, no matter how I fix them, I have P variables left, and let's look what happens to the bias.
But in particular, you're going to set P to be less than K?
P must be less. Yeah, it will be a prime between K and K minus something. Yeah.
But it won't be K.
I mean, if it's K, then it's great. But yeah.
So that wasn't known or something like that. That if K is say prime or prime plus 1 or something like that, then there must be.
But I'm not proving this either. I'm proving something else.
Okay.
I'm just going to show you some use of this thing.
This is not known. So
No, I don't. I have to think about it. Maybe we have a proof. Yeah. Okay. So what's the bias of G? So the bias of G will have to be equal to this bias, right? Now what is this bias? So let's write. So we have only P variables left. So it's 1 over 2 to the P choose I, and here we have I plus R, right? And now let's do the modulo P. Let's look at everything modulo P. So to do it, let's first move to the 2 to the P to this side. Okay, just multiplying. And see, this is constant. It does not depend on T or R. This is just the bias of G. So this is some constant number. And now let's do modulo P. So as I said, if I is smaller than P, then you don't have anything, right? P choose I is 0 modulo P if I is smaller than P. So unless I is 0. So P choose 0 is 1, P choose P is 1, but P choose I for other I's is 0. So this is what it becomes. So what did we get?
Wait, do you know the 2 to the P times the bias? I see. That's an integer.
That's something on the left. I don't care about it.
But you need it to be an integer.
Yeah, it is an integer. Why? Because this is an integer, right? Exactly. Good. Yes. So yeah, that's why I multiply, because this is an equality of integers. So I can take modulo P. Thanks. Yes. It's very important. Okay, so what does it tell us? For every R, which is at most T, right, because R is at most T, this value plus this value equals this thing modulo P. So it's constant, it's fixed. So think about it. R is very small. It's at most T, so it's roughly square root K. And P plus R is roughly, so you have connections between R's at the beginning and R's at the end, right? The value here of R and P plus R is always the same. So it gives you long-term correlation between values of the function. So if you think about constant function, of course everything is the same, but also parity, right? Parity, if you always go a fixed distance, you'll have either 1 and 1 or 1 and, right? If you go fixed. So, okay, great. So this is the kind of equation we would like to have. Yeah, this gives us correlation. But this is not something that we will use. We'll have to use something slightly different. But that just was a warm-up to show that, because this was very easy, right? I just wrote the bias, took modulo P, and immediately got interesting information. Okay.
But it's also helping you relate some very...
Yes, but
it's not the low degree terms here.
No, it's just values of G. That's what I get. But I want to show that G is eventually my goal will be to show that G is fixed on very large intervals. It will basically be fixed on the beginning, on the end, and around the middle. And then I will show you that this implies that it has a non-zero Fourier coefficient at a low degree. Okay, so let's do more things. So now I'm going to take, recall previously I took T to be K minus P. Now I'm going to take T to be K minus P minus 1. Why? Because it will be helpful. So again, if you fix T variables, P minus 1 variables left alive. And let's assume again that the bias doesn't change, because this is our basic assumption. And let's again write the equations. So now we have P minus 1 variables alive, and we have this T. Okay? So this is for every R smaller than T, right? Okay. So as before, I'm moving the 2 to P minus 1. So this is an integer, and this is an integer. And I'm taking modulo P. Now what happens to this modulo P? It becomes minus 1 to the I. Okay, good. So this doesn't seem to help, right? Because we still have P terms here and some number here. But let's look at it again. So I'll go here. So look at I plus R. The coefficient here is minus 1 to the I. But if I just change R by 1, then the coefficient, so I will get that the coefficient of I plus R plus 1 is minus 1 to the I. So the coefficient flipped, right? Think about I being 5 and R being 5. So this is 10, and the coefficient is minus 1 to the 5. Now if I look at R being 4, then to get 10, I should be 6, and the coefficient will be minus 1 to the 6, so it will be 1. So if you take two different R's, then in two different equations, the coefficient flipped. So what do we do in such a case? We just add the equations to cancel everything. So what survives? The first term and the last term, right? Because all other coefficients just 0. So the sum is constant.
But this is what we had before, right?
Almost. Oh. That's almost what we had before. What's the difference? Okay. Okay, yeah. It's what we had before. No, but you'll soon see why it's more helpful than before. I mean, it's, yeah, the way, I mean, it's like going to Ithaca. It's the way that matters, not going there. So it's, yeah. Okay, so what we learned is the following. Let's look at this term. This thing equals this sum. And this sum, what is it? It can be either 0 if both of them are 0, or 1 if it's 0, 1, or 2. So you know that this thing is in 0, 1, 2. Okay? But the point is, so what's the difference than before? Now we know that this is an integer. Previously, we just knew that 2 to the p is an integer, right? So we know that this guy, so this was 2 times some integer. So let's divide by 2. So this guy is either 0 or 1, or what is 1 over 2? This is 1 over 2. Okay? Modulo p. That's, yeah. So what did we learn? We learned that this ugly thing is either 0 or 1 or this huge thing, p over 2. Okay? Let's write it again. So again, so this is what we started with, and that's what we got, right? The gr plus gp plus r equals this thing, and the bias, the 2 to the p minus 1 times the bias, which is an integer, is one of those things, modulo p. Great. So let's look at the two different cases. Let's start with this case. It's ugly, but it's beautiful. What's happening here? So let's write this thing again. So you remember, so this is f p plus 1, it's the bias of g, it's this guy. But this guy was what? It was this term, right? That's how we got it, remember? So let's open it. So gather the positive coefficients and the negative coefficients. Okay, now, how many coefficients do I have, how many summands do I have here? P plus 1 over 2. How many I have here? P minus 1 over 2. So this is an integer between 0 to p plus 1 over 2. This is an integer between 0 and p minus 1 over 2. And the difference has to be this guy. How can it be? Either this is 0, and this is p1 plus 1 over 2, or this is 0, and this is negative. And because we are modulo p, I mean, it will be the same. So let's say that this all 0 and all of these are 1s. So it says that you are 1 at r, you are 1 at r plus 2, you are 1 at r plus 4, you are 1 at r plus 6. But on r plus 4, on the odd ones, you are 0. This is the parity function. So this case, here it comes, right? Somehow in the theorem, we'll have to rule out the fact that G is parity, right? I mean, our theorem says you have a low-term thing if you are not parity. Here it is. That's where it comes up. So, okay, so we rule this case out. So if this is not the case, then this is the case, right? But I claim that this implies that previously we just added the sum of the values is constant. Now I tell you that the function is fixed. Why? So let's look. So we know that this thing is in 0, 1, right? Let's go up.
Oh, it's fixed and independent of R.
Independent of R, it's fixed. It's just some constant depending on P. Why is this? Because let's look at our initial equation. 2 times, the sum is what? Is 2 times this thing, right? What is 2 times this? It's 0 and 2. The sum of 2 Boolean values, how can it be 0? Both of them are 0. So, or it can, and how can it be 2 if both of them are 1? So if this thing is 2, then all those values should be 1. If this thing is 0, then all the values should be 0. That's it. So what did we get? G is fixed, all small up to T, or all large, because between it's P plus P, right? So it's fixed on those 2 intervals. Great. So that's the conclusion that you get, right? That if G is not parity, then for every R smaller than T, this equals this. Okay, so we know that the function has to be fixed at the beginning and at the end. Good. Okay, now we'll have another, still have, almost last slide. I mean, that's the last slide of the proof. So that's what we have. We have that the function is fixed at the beginning and at the end. Okay, now I want to get more information. I want to show that it's fixed around half. Now it will be easy. I mean, it's just this slide, right?
Something is strange just in the monotonicity, because if you made this k to the 0.525 smaller, it seems
yeah, so actually, no, I didn't give you the exact parameter. P is, I think it's...
but you would have to assume that
this is
no
think about 2 times this, or
guide
all
there.
of this. I mean, I don't give, okay, I just... I'm not cheating, but just like there are some hidden constant that I'm not putting.
No, but you could have assumed this thing, instead of k to the 0.525, at k to the 0.7. That's a weaker
terrible
assumption,
yes.
But then you would
get
something
no,
weaker.
right. It's, yeah, but 10 times this thing is enough, or something. Yeah, I mean, just don't worry about this, okay?
Yeah, it's fixed on the interval like 0 to t over 2 and
or
k
some,
minus
yeah.
t over 2.
Exactly. Okay, so now I want to understand that part. And to understand this, I will just pick a prime around this and work modulo twice this prime. So I pick prime q, which is around this number, and look what happens when I set k minus 2q variables. So again, it will be roughly this many things. So again, I write the bias and multiply by, I already did the multiplication. So this equation is the same thing, right? And I take modulo q, so now we have 2q. Remember, we also analyzed this case. Now we have a sum of 3 things. But look at this. This is a small thing, and this is a small thing. I already know that they are fixed, right? So this guy is basically this thing plus some constant. Or in other words, this is a constant, so I know that guy, right? Okay, so it must be that value, or in other words, some other constant. Okay, so that's what I wanted. So now I have that you are fixed at the beginning, you are fixed at the end, and you are fixed in the middle. And now, okay, so that's what, but that's the important thing. That's what I wanted to get, actually. Because basically, most of the weight comes from that part. And intuitively, if you are fixed there, and let's assume that you are equal to 0, because I can look at the 1 minus the function. And if this is most of the weight, then if you slightly shift it around, the weight will dramatically change, because you are 0 there, and now something entered. I mean, things will go wild. And this is captured by the following thing. If G is fixed on this interval, then fixing 2 variables changes the bias. That's it. And now, this will be in contradiction, because fixing t variables shouldn't change the bias, right?
So for this part, you're even forgetting the fact that you were fixed at the
Yes.
end.
So unless G is a constant, right? Because there's always the caveat unless G is a constant. And why is yeah. So this means that there is some non-zero Fourier coefficient, but it doesn't matter. It's already a contradiction. And what's this? So basically, it follows from the following simple fact that this number is at most this number only if I is in that interval. So for larger I, this is always larger than this. How do you prove it? You just calculate. It's simple. It's one line. Everything is one line. It's long lines, right? Okay. So, but it means that basically, because this comes as the coefficient in the bias, so the coefficient, the contribution of this guy, of I to the bias, is always larger in Gn compared to this guy, right? Because let's just write it. The bias of Gn, this is the coefficient. And here, if you do the calculations, this is the coefficient. So that's it. Good. So that's the end of the proof. Okay. So yeah, I mean, it's fast and it's a lot of modular calculation, but okay, let's just do a recap, because I mean, there was a lot of calculations. All of them are very easy, but the lesson is that if you have equations over the integers, working modulo primes is very helpful, even if you don't use the Chinese remainder theorem. Okay, so we ask the question: what is the minimal degree of a minimal term? What's the degree of the minimal term in the Fourier spectrum of G? And we looked at the bias, and we used the theorem of Shao and Massey that says that basically this is all of those are zero if and only if the function is somehow resilient. I mean, is not affected by fixing a small set of variables. And then we studied the function modulo different primes. Basically, we studied these kind of restrictions, and we concluded that the function is fixed on very large intervals, especially fixed around the middle, which was the most important part. And then we concluded that this thing is not equal, which contradicts the assumption. Okay, so what's next? That's the last slide. How to improve? So here's a theorem. I'm not going to prove it. So now we consider polynomials into 3 values, not 2 values. So if you could show that any such polynomial has degree at least k minus s for some number s. So remember, von Zurgaten studied degrees of function into 0, 1 and showed that it's at least k minus k to the 0.5 something, right? Just assume that you could prove something similar to 0, 1, 2. Then it will say that any symmetric nonlinear G has some small Fourier coefficient. This is for Boolean. This is a non-Boolean, but this conclusion will be for Boolean functions. So in order to understand Fourier spectrum of symmetric functions, you need to understand functions into that take 3 values. So what's known about this? So the best thing that's known, it's also a joint work with Gil Cohen and Avishay. Oh, I didn't mention. Did I mention Avishay? Okay, it's a joint work with Avishay Tal, and this is a different work with Gil Cohen and Avishay Tal. So we show that the degree of any such age is at least k minus little of k, but this little of it's too large, but still it's something. And what are open questions? Okay, obvious. I mean, improve this, improve that. I mean, junta, many open questions. So.
You have symmetric functions that don't have Fourier coefficients of weight 1 and 2? Or?
Yes, but they don't have example. They don't have weight 3. Okay, so yeah, thanks.
Did you resolve what the F was for?
Sorry?
Oh, never saw that.
Yeah, let's, what did they do? It will come in a few steps. What F was for? I need okay. You see this little at? So I found a font that has G at and H at, but doesn't have F at.
No, but you know
It
that
wasn't clear.
You know that in PowerPoint 2010 there is a great equation editor.
I know, but that's another thing. My office laptop has 2010. My office computer, but my laptop has 2007. Preparing the presentation 2010, moving to 2007 is something I don't. Yeah.
You don't recommend.
Yeah, I don't.
You
Yeah.
can get a good deal on Office.
I already yes. I noticed that point. Yes.
So
Okay.
just if I want to, like the last point that you said, is if a function is constant on like an interval around half, then shifting by 2 will
Change the bias.
If I want to think about it probabilistically, is because once you go beyond this band around half,
You can distinguish.
Changing by 2, it changes the probability by so much that if you look at like the, say, the closest to 2 thing that has 1, say around it will increase. Like you can increase the probability of being 1 significantly.
Yes, yes. Basically, it's this range. It's monotone. I mean, just shift fixed by 1. It changes the probability. I mean, everything increases. Like it's like.
Increases a lot. Yes.
Yes, it just goes.
So how much did you need the band to be? How fat do you need it to
Square root
be?
k.
Oh, you do need
yeah.
it to square root of k or something. And
That's,
that's like
yeah.
Chernoff time for
Yes, that's for this kind of argument. Yes.
So,
Yeah.
So, and on your last slide, so do your bounds work if your polynomial is just a 0 and 1?
Sorry. So.
if you just wanted to take two values,
Yes.
to improve.
Yeah, so we can show that if the function takes two values, then its degree is at least that much. But in order to get something better, we have to have something that's smaller than k to the 0.525.
Yeah, no, sorry. I'm sorry. This is if it takes three different values.
Yes.
What if it just takes two?
0 and 1. So that's von Zurgaten-Roche. That's k minus 2 to k to the 0.525. But it doesn't give me enough info. But I don't have either. But that it only implies things for functions that are unbiased. But for biased functions, it doesn't imply anything. This implies for both biased and unbiased. And the price that we pay is like that you have to prove something for more functions.
Regardless of Kramer conjecture or something like that, you don't know how to.
So in the conclusion, you also get that S is not empty?
Yes.
So even if Kramer's conjecture were true, you don't get log squared
No,
k.
I have
you still have the
square root
of
k,
bound
yes.
square root of k.
Yes.
I see. Okay.
That's why I said ERH, not Kramer.
So with this, the hope is that the true answer is much better than you get with all this here.
Yes. Yeah, I mean, right now we use number theory because we don't have any other idea.
Okay.
So this bound that shows, is it also based on some number theory, or is
This? Yes, and actually, I recommend the paper. I can give a marathon on it at some time. But the log k, basically, I have to say it, and then you'll be free. We find a Boolean cube of primes. Namely, we find a structure that is like a Boolean cube. So you have k directions. Each direction is an associate integer. And the 0 point is also an integer, such that no matter which subset of the integers you add up to that integer, you get a prime number. And we take the equations modulo all those primes, and then we get something. So it's a lot of number theory. The number theory just guarantees something about. We don't just need the existence of a prime, but rather how many primes exist in any interval. Then we realize.
Like probabilistic method of
Log k cannot give more.
So you have P1 to P sub L, and any subset of these sum up to.
No, it's not P1. I have P1 and then delta 1, delta 2, delta L, and P plus any subsets of the Li is a prime number.
Okay.
Yes.
And the kind of result that you use there is to bound what is the PI.
Yeah, so again, I look at so I assume the degree is small, I get many coefficients, I study the modulo all the primes, I combine them in some magic to get some easier equations, I get something. And then I complicate the thing so that the reader will not understand something, and you get the result. And
the structure exists.
Sorry?
The structure of this.
It's just it's a cute argument, but you can do it. It's some induction.
For any number, you can find the structure where the.
Yeah, basically you start with 0 cube, which are just prime numbers, and then you use pigeonholing to prove that there exists one-dimensional cubes, two-dimensional cubes. Yeah. But that's for another time, 3-hour talk, and yeah, you're excused.
All right, thanks.